Hello, Wildcats. I hope everyone is doing well. This is just my overview tutorial of Unit 8, Focus Question 3, Applying Newton's Laws. In reality, we've actually encountered all of these laws before. Obviously, Focus Question 2, we saw Newton's second law, but we've actually talked about, without specifically naming them, the first and third law as well. So this focus question and final focus question of Unit 8 is really about putting them all together. So let's get started. Newton's first law of motion, according to, in Newton's exact words, are, quote, every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. So in other words, what we commonly call that is objects at rest stay at rest, and objects in motion stay in motion, unless they are acted on by some force. We've heard that many times before. We heard that at the start of this unit. We know that what causes objects to accelerate, in other words, speed up or slow down, is an unbalanced force, right? So when we talked about net force, we said if net force is zero, the object's motion stays the same, or in other words, it doesn't accelerate. So when forces are balanced, if the object is at rest, and in other words, its velocity is zero, its acceleration will be zero, which means it stays at rest. When forces are balanced, objects that are in motion, in other words, their velocity is not zero, will have no acceleration, so they won't speed up or slow down. In other words, they stay in motion. So we need some net force that is not zero. So that's where it comes into, unless it is compelled to change by forces. So when a force acts on an object, it causes an object to accelerate. If there is no net force, it keeps whatever motion it currently has. In other words, it doesn't accelerate. So objects do not change velocity or accelerate without an outside force. So this ball will just sit here unless an outside force acts on it. And this one will never stop unless an outside force acts on it to speed it up or slow it down. And that, in essence, is Newton's first law. We commonly call that inertia. Inertia is described as the tendency of objects to not accelerate on their own, or in other words, maintain their state of motion. So when net force on an object is zero, the acceleration is going to be zero. So inertia is really just a property of an object that it has that represents Newton's first law. Objects in motion stay in motion, don't accelerate. Objects at rest stay at rest, don't accelerate, unless some outside force acts on them. So let's just check about thinking about what that means. Here we have a textbook, it's at rest. Someone pushes it so it has a velocity of 1 meter per second, and it slides across the table, but not long after the book comes to a stop. Which statement best describes why the book stopped? Is it that there is no force on the book? In other words, once the student stops pushing it, it stops. Or is that there is some force, and that's what stops it? So Newton's first law tells us objects will continue doing what they're doing at rest or in motion unless a force acts on them. So if this book is moving and then stops, it must be due to the presence of some force. And we know, so we've got two choices here, without a force being applied, the book is no longer pushed, there's nothing to maintain the book's velocity. That's not accurate. There must be some force. The presence of some force, we know that force is friction, causes the book to change velocity. In other words, to go from some velocity to no velocity. That's acceleration. Acceleration is due to force. So why is it that some objects have a tendency to resist changes to their state of matter different than others? So if I have two buckets here, one's empty and one's filled with sand, this one's going to be much more difficult to push. Or an object that is really heavy or massive is going to be harder for a person to stop than an object that's lighter, right? It's going to be much harder to stop a moving car than it would be to stop a softball rolling down the street. And that is because mass, or the measure of an object's matter, also is a measure of how much inertia it has. So the more mass of an object it has, the more inertia an object has. And that makes sense if you think about it, because force, acceleration, and mass are all related. So we saw in the last focus question, the more mass, the more force it takes to cause that object to accelerate. So the more massive an object, the more it resists changes to its state of motion, so that's a direct relationship, right? This is a very massive object so it has a lot of inertia. It would require a large force, or it would resist changing its state of motion and require a large force in order for its state of motion to change, in other words, for it to accelerate. So there is a direct relationship between inertia and mass, and inertia is just a way to describe the tendency an object has to maintain its state of motion. So the more massive an object is, the more it resists that change. What does that predict the amount of force? We just talked about that. The more massive, or the more inertia an object has, the more force required to change its motion, right? And we just used this exact same example. Okay, Newton's second law we'll cover briefly because we just did that in the last focus question. So we know acceleration is equal to the force applied to an object divided by its mass, right? So this is where we can see Newton's first law come into play again. So those two are related here, right? The more massive or inertia an object has, the greater the force is needed in order to get it to accelerate. We saw in our last unit, or last focus question, that mass and acceleration are indirectly related, and mass and force, or acceleration and force, are directly related. So just a quick review here again. Why does the baseball go farther than the bowling ball? Assuming you could hit a bowling ball with a baseball bat, would be this object is much less massive, so it has less inertia, which means, assuming the same force is applied, this object will accelerate greater, or have a greater acceleration. Greater acceleration means more velocity. More velocity means more displacement. And so now we're getting back into kinematics. Whereas this object is going to resist that change. More mass means if the same force is applied, less acceleration. And then, so here's just a visual representation of all that as well. If a hand is accelerating this brick, twice as much force means twice as much acceleration. If I have twice the force and twice the mass, I would have the same acceleration as this picture, as the top picture up here. And this just works down that same thought process, but with mass. So here I double the mass, my acceleration would 1/2. If I have triple the mass, my acceleration would be 1/3 as much. They are inverse. Okay, so thought experiment. You can go and do this if you want. Pause the video. Put yourself in a rolly chair and take an object. It doesn't have to be a bowling ball. This is me lounging in my rolly chair in my office doing e-learning. But if you have a rolly chair at home, or a skateboard or something, go stand on it, something with wheels. Go stand on it and take a softball, a baseball, your physics textbook, whatever, and throw it away from you. And what happens? This is me pausing so you can go and do it. Okay, I'm glad you're back. So if I were to take this and to throw this ball this direction out of this chair, what would happen to me? What happened to you? So you probably found out that when you took this object and threw it away from you, you went the opposite direction. Why? This is Newton's third law. So Newton's third law is all about interacting forces. So here's me on my skateboard, safety first, wearing my helmet. I throw this object away from me. When I throw the ball away, I apply a force to the ball. We know that. But what we need to stop and think about is that the ball also applies a force to me that is equal and opposite. And these are called action and reaction pairs. So if I go back up here, when I apply a force to this ball, let's just say it takes me 10 newtons of force to push this away. This ball also pushes back on me with 10 newtons. And therefore, my mass has a force applied to it and I accelerate. So just as the ball accelerates, I accelerate. And that's why you see what we experience when we throw something, if you're in a chair or whatever, or two people push off of each other, they're experiencing Newton's third law. And this is called action and reaction. So we know Newton's third law is commonly said as For every action, there's an equal and opposite reaction. This is what we mean. For every force, there's an equal but opposite force. So let's think about how that plays into this scenario. If this car drives into this wall, we could say the car applies a force to the wall, right? The car is driving into the wall. But Newton's third law tells us that the car applies a force to the wall, so therefore the wall must apply a car to the force. The wall must apply a force to the car. So if those forces are equal and opposite, if this car drives in and hits the wall with 1,000 newtons of force, that means the wall applies 1,000 newtons of force in the opposite direction. So the question, when a car exerts a force on a wall, why does the car get damaged? Well, it is because Newton's third law tells us the wall also exerts a force on the car. And because the car has soft parts, squishy parts, not like bricks, it will get damaged. Those parts will crumple because of the force acting on them. In other words, the car accelerates in to the left. The car parts accelerate to the left because of the force from the wall. So when objects interact, they exert a force on each other. And we know this, right? This is the normal force. We talked before, there is a force, the force of gravity pushes an object down into a surface. Well, the normal force is the surface pushing back up. So really we've talked about Newton's third law, we just didn't call it that. And what we're seeing is this force, this normal force, is the reaction force. So we have action force and reaction forces. The action force is the one pushing down. So if I go back up to this picture, the car is the action force. The reaction force is the equal but opposite force due to it. So the weight of this object, the force of gravity of this apple, pushes down on the surface, and therefore the surface must also push back up. And so we have action and reaction forces. It's worth noting, it depends on what we're talking about. I could say that the table pushes up on the apple, that's the action force, and so the reaction force is the apple pushing down. And it just depends on our perspective. So we need to think about what is the object of interest. In this case, the object of interest is the apple. So I would call the apple pushing down the action force and the normal force, or the table pushing back up, the reaction force. If my object of interest was the table, then the action force would be the table pushing on the apple, and the reaction force would be the apple pushing down. They are the same, it just depends on which way you're looking at a problem. So, Newton's third law says, if two objects interact, the magnitude of the force exerted on object 1 by object 2 is equal, but opposite in the direction to the force exerted by object 2 on object 1. In other words, for every action there is an equal but opposite reaction. For every force there is an equal but opposite force. And so here's a ton of different examples, right? When you push on a wall, the wall pushes back on you. That's normal force. If you are skateboarding, why do you move forward? Well, you push on the ground pushes back on you. Anyone, if you've ever shot a shotgun or any type of firearm, you know that there is the action force, the force from the gun on the bullet that sends it out, but then there's an equal but opposite reaction force, and then you feel that, we sometimes call it kickback, and you feel that in your shoulder and the gun comes back. Or if you've ever seen a cannon being launched, right? I mean, there's a big explosion out, but then the cannon slides backwards too. Here are two physics students having fun in rolly chairs. If this student pushes off, yes, we know this student will go this way and accelerate to the left, but this student will accelerate to the right. Why? Because the force applied by student Beard on this student will be equal and opposite to the force that this student applies on the student with the beard. That's how a hammer and nail work. If you've ever been on a boat, and you jump off a boat or a canoe, you know that the canoe wants to move the other direction. It does accelerate the other direction. So the applied force is the action force, and then the normal force or is the reaction force. And we could go through, there's many different examples of them. Here's another one that I think we're familiar with. If you have a balloon filled up and you let the air out, right, that's the action force. As the air comes out, it accelerates the balloon in the opposite direction. That's how rockets work. Literally, they cause explosions that shoot hot gas out. That is the force. Those gases being expelled create a force, which then causes an equal but opposite force on the rocket, which causes it to move up. And so literally rockets going to space are just Newton's third law in action. We said this before, right? You sitting on a chair, this is the action force, and so therefore the chair pushes up. That must be the reaction force. We talked about this briefly as well. Action-reaction forces act on different objects. So here's two students on ice skates, and student A pushes on student B. Student B, there is an equal but opposite force on student B. So if student B is just standing here and student A pushes off of them, they will both accelerate. Why? Because there is an equal but opposite force. And so here we can think about which object we're talking about, right? This is the force of the hammer on the nail. There is an equal but opposite force from the nail on the hammer. So then why is it when you hit a nail, the nail goes in and the hammer doesn't go bouncing back terribly fast? In fact, it kind of just slows down and stops. And if we stop and think about it, it's because the hammer is more massive, so therefore it has more inertia, and therefore it resists that acceleration greater, whereas this nail is less massive, so therefore the same force applied to both of them will cause greater acceleration here. And so we really need to be aware of what is our action force. In this case, the action force is the force applied from the hammer to the nail, but there is a reaction force from the nail to the hammer. And they are, as Newton's law tells us, equal but opposite. So it says in red here, the action-reaction pair never occur on the same object. That's true. The action force is the hammer to the nail. The reaction force is the nail to the hammer. And like I mentioned briefly at the start, this explains why the hammer stops, right? If the hammer is going to stop when you hit a nail, why? Well, objects only speed up or slow down, in this case the hammer stopping, when some force acts on it. So what stops the hammer? What stops the hammer is the force of the nail on the hammer. That force causes it to accelerate / slow down / eventually stop. And so Newton's third law explains a ton about the way that we see the world around us. All right, last one here. It's kind of a weird one to think about, but interacting forces propel you forward each time you take a step. So it is Newton's third law that allows you to even move around. So when you walk, you apply a force down onto the ground. But the ground also applies a force to you, right? So here is the force of you on the floor, and then the force of the floor on you is actually what moves you forward. So as weird as it is to think, it's not you pushing on the ground that makes you walk. It's not your applied force directly. It is the reaction force. It is the ground pushing, literally pushing you forward, that causes you to move forward. That is an action-reaction pair, and it explains how you move forward. So why doesn't the earth move under you each time you take a step, right? I mean, if I'm pushing on the earth, then shouldn't the earth also accelerate? The reaction force is causing me to accelerate, so why don't I cause the earth to accelerate? Well, if we go back to Newton's first law, we know that the earth has far more inertia or mass, right? So if this reaction and action force are equal, right? When I step, I apply 50 newtons of force to the ground, and the ground applies 50 newtons of force to me. So this is 50 newtons. I have some mass, and so therefore I accelerate due to that 50 newtons. The Earth has a huge mass. Compared to us, it should have made this M the size of the page. But it has a huge mass. And because those forces are equal, but yet this mass is huge, it means the Earth is going to have a teeny tiny acceleration. And an acceleration that is so small that it's basically zero. There's actually one of the practice problems from this week relates directly to that. And so you can get a chance to see how small that number actually is. So hopefully that helped. To go all the way back to the first slide here, there are Newton's 3 laws of motion. The first law, every body remains in a state of rest or motion unless acted on by a net force. That's inertia. The more massive you are, the more inertia you have. Newton's second law we've seen. The acceleration of an object is directly related to the force applied to it and inversely related to the mass. And the third law, for every action there is an equal but opposite reaction. So in other words, if I am pulling on this leash with 10 newtons of force, then the leash is also pulling on me with 10 newtons of force. So I hope that helps as you go through your notes. Please let me know if you have any questions, and I hope you have a good rest of your week.